Okay, so we will continue. So this is the topic for today's class. So we will look into partial state information and belief state, and then we will look into multi-agent problems, some example on multi-agent problem, some basic idea about MPC, and then we will also try to relate DP with RL. So to define or to motivate belief state, first we need to understand what exactly was state variable for us. So as we understand, state variable is the information needed to model a system from time t onwards, right? So this is the key, right? Information needed, right? So all the information that you need to model a system, we define it to be state, right? So this makes the state variable more sophisticated, because then you can ask what all informations you can gather to define a state, right? So naturally, with this generic definition of state, the definitions do vary across communities. So if you ask some control theory guy, then they might define it in a different way. If you ask someone who is more into, let's say computer games, then for them the state's definition may be defined in a different way, and those working on broadly in, like, let's say some other computational domains. So for an example, if you look into this, then one can ask, what are the information you track for a robot navigating a room, right? So here we can think, what could be a possible state? What all information I need for the problem of a robot navigating a room? So there are various perspectives. Like if you look into MDP, so here according to Bellman, who was the initial, you can say he was working mostly on dynamic programming, DP, and so basically, so he invented in some sense the dynamic programming. So according to him, a physical state system characterized at any stage by a small set of parameters is a state. Okay, so this is the definition of a state according to Bellman. So a physical system characterized at any stage by a small set of parameters. And then according to Butterman, at each decision epoch, the system occupies a state. So depending on like when you are going to make a decision, there we say that it occupies a certain state. Okay, so there is more to be elaborated here. So not very like completely clear, right? But if you look into RL literature, so this is the standard textbook, Soderman and Bartow, then they define state to be all aspects of the past that make a difference for the future. So this is kind of generic definition of state, right? All aspects of the past that make a difference for the future, right? So all aspects here could be like all the information that you may need. So yeah, of course, with each of these definitions, there are various there are common problems. Like some definitions could be circular in the sense that state is defined by using the word state itself. Some definitions assume full observability. So this is something we will see in this class today. What is full observation, right? So what do we mean by this? I will define that more precisely. They do not always account for missing or probabilistic information. So in some cases, they ideally we should have in the state definition, we should also include something which is missing, but also there is some probability. There is some probability of something missing, let's say, or something appearing in future. So these are the things. So there will be some uncertainty that we should also take into account when we define a state. So this is what this point means. So and then Professor Powell, he has his own definition. Like so in his website, he has defined like various ways of like people define states and how he thinks it should be defined. So one could be like policy dependent version, a function of a so a state is a function of history that combined with exogenous information determines the cost, policy, and transient function. And we can also have like optimization versions, a function of history which is necessary to compute the cost, constraints, and future transitions. So So if we could distill the state information into, let's say, 3 variable, we can try to, and this is what we will try to do today. So state itself could be defined by, let's say, 3 variables. Physical state variables, so these define the physical state. So for example, observable states like inventory location, so this is like the physical location of the agent, let's say. Okay, and another part of the state variable could be let's say informational variable, and these could be, let's say, external data as market prices. Okay, so these are some, let's say, some external data which could also be part of the state variable. And so this may not be a physical as such, but some information that I can take from outside, we can also kind of call this as information variable. And we can have some belief variables. So belief variables are like probabilistic belief about uncertain quantities. So we need to somehow in the state incorporate uncertainties as well. Okay, so this is what belief variable means. So for example, in this quiz, let's say in a self-driving car, which of the following is a state variable? Okay, so this is question 1. So is speed of the car state variable? Is it is it in one of these categories: physical state variable, informational variable, or belief variable, right? Speed of the car, so what is the current speed of the car? Traffic light color, so this is some additional information that I get from some external information that I get while looking at the traffic light. Weather conditions, so that's also an information that I should be able to use if possible in my state. So this is of course this is something, there is uncertainty involved. Okay, so this is pretty much in the belief state, belief variable, right? So what is the prediction of the weather? This does belong to some uncertain quantity, because weather is not really very known with certainty. So these are all part of the state variables. Okay, so these are the ways, like we may need to think about the problem we are given at hand, and what are the states and additional information that we can include. So as an additional question, you can look at, let us say you are doing clinical trial modeling for drug effectiveness, right? So you are trying to create a drug for a new let's say viral disease, and then you need to do some clinical trial. So what are the states in this? What are the decisions you're going to make? Could be one of these. Okay, so in this case, let's say for clinical trial modeling, then you may look into physical state variables. So number of patients involved in your clinical trial, doses, levels administered, like how many, what was the volume of the dose, maybe if it's in liquid form, and then patient health status. So it could be, let's say, various health status we know. It could be blood pressure, it could be some other factors. Maybe you may have a full test of the patient, and you know all these parameters. Side effects observed, and trial budget remaining. And information variable could be, let's say, medical guidelines that is set right now that you are supposed to follow, public health trends in general, what is the trend in the public, which could be related to the public you are involved with. Okay, so like certain during COVID, there were certain research that said that certain group of people are kind of overall they lack in, let's say, vitamin D levels, and viral disease have more effect on those with vitamin D deficiency. So these could be some of the trends that you may look at in the wider population, where what are the possible health trend in the community surrounding the area where you are going to do the trial modeling. And patient dropout rates, so at what rate patients drop out from the trial midway. So you may have these informations. Regulatory approval, so this may come from the medical agency, under whose guidelines, under whose regulations you have to you have to follow, and whether those approvals are there or not. So, and belief variables could be effectiveness of the drug. So this is your belief that how good the drug administered will be effective for the current disease. Likelihood of side effects, this is also part of the belief. So there is likelihood, this is a probabilistic estimate of what could be potential side effects. So these are the things you will factor in. Long-term patient outcomes. So what could be the long-term patient outcome? So these are uncertain things in your model. Okay, so you don't really know very precisely. And the true placebo effect. So how could the patient might respond to the administered drug? So given a problem at hand, the way you will model the states can be broadly classified into these. Of course, problems come in a wide variety of complexities, but in general, you should be able to kind of encode your state variable in these three forms. So physical state variables, informational variable, and belief variables. So belief variables covers all the uncertain part of your model. So why does partial observation matter in decision making, right? So some more examples, a man walking in fog with limited visibility. So it could be a case where you are walking and the weather is such that it's foggy and you have certain belief. What you can measure is your limited visibility in your current state. So you can only see, let's say, until this point. And then you have a belief for the future that the road kind of continues in future. So that's your probabilistic estimate that the road continues in future. It's also your probabilistic estimate that maybe the road doesn't end as soon as immediately. So you may it doesn't close basically. So you may indeed continue with this road. So you may think of many such possibilities that that even here when you're walking and making decisions, then you have certain belief in your mind that you will consider that as a part of the state, and then you will make a decision to continue along that path. So it could be similar situation in robots. So of course our whole goal is to transform everything into autonomous agents, which could be robots. So what we do, we have our own estimates and whatever, but then can we encode these things into a computer program, and so that the agents can robots can also have something similar. Okay, some similar belief states and so on. So if we translate this to robots, then maybe robot is in a smoky room, and then the sensors are kind of not don't have a full visibility. In this case, let's say visual sensor doesn't work that well. Maybe other sensors also may have limited things. So you made a robot with some set of sensors. So let's say in this case visibility, but you may encounter a case where you have limited visibility, and then still the robot has to be robust enough to continue in the decision making. Okay, it should not kind of stop. Okay, so belief state could be also this case where you are playing chess with blindfolded. So here your belief state will incorporate also some amount of memory that you had from the past, that you played certain positions in the game, and you also kind of remember the opponents and so on, and based on that you have some estimate. So here is like you are not able to see precisely the state, but here you may rely on some amount of memory and how much you trust the memory. So this could be also kind of seen as your own belief. So miscalculated belief can be fatal, we know that. So there was a case recently of this case, a car accident happened where there were like couple of people who were kind of following Google Map, and then there was an incomplete breeze, and but the Google Map said that this is a road they should follow. They continued on that route, and then later they found out it was a night time, so the car visibility was limited. So this is kind of one of those cases where it's a belief state where you trust the sensor. In this case would be your limited visibility for the car in the night, and you are also following Google Maps and so on. So there was a certain amount of belief that you want to continue in the road, and you expect that the road will continue, and these are the things you don't expect in general. So you had the estimate that like 99% of the time what Google suggests is a correct route, and you are supposed to follow even in the night time. Okay, so this is again part of the belief, and it could be fatal. Okay, so so from robotics to healthcare, agents must act optimally despite incomplete and uncertain information. So at best what you can do is try your best with the best possible estimates of the belief despite having uncertain information, and still you should be able to kind of propose some solutions out of that. Okay, so this is how real life works. So handling partial observations, as you know, I have well motivated you by now that partial observation is the fact of life. Whether it's a clinical trial, whether it's path planning, these will be the situations where you will be encountering partial observations, a lack of full sensor data, and still you should be robust enough in making decision making. Of course, there is a possibility that 0.001% something might go wrong, but this is a fact of life. Sometimes things do go wrong, but as best you have to try as best as possible in whatever decision making you do. Okay, so but we do want to incorporate this, codify these things, right? So we know that when we say belief states, then the moment we say that, it's an uncertain thing, right? But then this is where probabilistic and statistical tools will help us even model those uncertainties. But otherwise we may say, why should I care? If something is uncertain, why should I even care about a model and go about that? But then we have to be as close as possible to the real life example, which does work with uncertainty. So let us formulate this as a part of the model, where we do encounter partial state information, and we will form something called belief state. So our assumption so far has been that the controller can access the exact value of the current state xk, leading to policies built on sequence of functions of xk. So we have xk, and then we have certain observations, and we go to xk plus 1 and so on. But then here we also want to incorporate the belief. So in real world scenarios, this assumption might not hold because some components might be hidden or not observable. Okay, so this is what we want to model. So sensors responsible for measuring state might be flawed or provide inaccurate data. Acquiring precise measurements might be prohibitive. So there are various scenarios, as you can see, where we may want to incorporate some belief state. So controllers in certain situations can access only subset of the state components, and these may be influenced by the stochastic uncertainties. A practical example includes three-dimensional motion problems. So this is just an example where we may have these cases. So all this leads us to a dynamic optimization framework, or the sequential decision making framework, which we call partial observable MDP. So how can we extend our dynamic optimization framework where partial observations are there? So basically the partial or the imperfect state information is because we have incomplete or flawed state data. So those are the things we want to model now, and obviously this has been a continued work, and these are some of the sources where these things are discussed. So so what we are interested in is POMDP, where it's called partially observable Markov decision process. So exact solutions of POMDP are typically infeasible because of the nature of the problem. Incompleteness, stochasticity makes it very hard to have exact solutions. So POMDPs are usually solved using approximate methods. Exact solutions are only possible in some specific cases. So the computational challenges are, so in general, problems involving partial state information do not differ significantly from the problem with perfect state information, at least from, let's say, from algorithm point of view. Once we incorporate this, the similar DP algorithms that you have followed might be useful to solve these algorithms as well. So a lot of effort goes into defining the state properly, but once the state is defined, you can still use the existing algorithms of rollout and so on that we have discussed so far. So by employing various reformulations, it's possible to simplify the partial information. So since we are working with a partial state information, what we really require is something called sufficient statistics. So basically, when you are working in a partial state information, what you have is whatever the partial information we have, and you will build some statistics based on that. And is that good enough to describe the state you are in? So once you have a sufficient statistics established, and an exact DP problem can be formulated on that, and broadly a sufficient statistics is a measure that captures the entirety of the information up to the time k, which is relevant for the problem at hand. So one possible sufficient statistics, we can call it a belief state, and we denote it by BK. So BK can be called as state in our DP problem now. Okay. So let us see an example of DP in a bidirectional parking problem. So parking problem we have seen before, but let us look into this bidirectional. So as the name suggests, you can go forward, but you can also go backward. So a driver is looking to park a car. The route consists of n parking spaces, and then at the last there is a garage. And unlike the simpler model, the driver can traverse both forward and backward. So this is slight extension of our previous parking problem. So what are the cost and the conditions involved in parking? So the cost Ci, if the space I is unoccupied and you do decide to kind of park at the space I, then the cost you will provide is Ci. And movement, in case you don't, let us say I and I plus 1, and if you do park at I, then the cost you will pay is Ci as before, and it has to be unoccupied obviously. And if you do decide to move ahead like this, then moving ahead now has a cost Ti. Earlier we did not have this cost in the previous example, but now we say that if you I mean in both ways, okay. So if you move ahead, so this is this point, if you go to the subsequent space I plus 1, this cost is Ti. If you move to the previous space, you decide to go back, then the cost is Ti again. Okay, so in the previous model we didn't have this. So the driver, in this case, the driver maintains a record of the occupancy status for the spaces they have passed and can revisit any of them. So driver is kind of maintaining the history from the previous states that the driver has seen, and what were their state, right? So whether they were free or not free. Okay, so this is a kind of a belief that the driver has, that the parking space previous ones were free or not free. Okay, in the meantime someone might take up that space while the driver has come to stage I, but still there is a belief that okay, in the previous spaces some were free. Okay, so what are the considerations? So likelihood Pi of the space I being available can also fluctuate over time. So this is also interesting extension to the model, that the likelihood of the space I being free is now also fluctuating over time. So this goes well with what I just said, right? So the driver is at I, and the driver can move in future to I plus 1, or it can go back to I minus 1. So driver has a knowledge of, because driver is kind of, let's say, going through this sequence of I minus 1, I minus 2, and so on. So let us say this was free, this was not free, this was free, this was not free, was free, and so on, right? So the problem for the driver is to consider parking at the current I, and if it is in this case, since the cost determines everything, so overall the driver is thinking about the cost. So is it worth parking at the current state I? Since the driver is allowed to go back, the driver may also estimate what could have been the cost. So let us make it free, let's say, for the moment at the ith. So if it parks, then it is Ci is the cost that the driver will pay. Okay, so but then this was the cost at I minus 1, and it is free. At least in the belief state, it is free. Now the driver, if decides to go back, then the cost will be Ti to go back, right? So this cost of going back plus the cost of parking at I minus 1 should be less than Ci. Then it's worth, let's say, parking at I minus 1 and not I, right? So the cost at I minus 1 plus Ti should be less than, so let us say strictly less, otherwise there is no point, right? So this is less than cost at I. Then the driver may decide to go back and actually park at I minus 1. Now what is additional problem here is that the probability itself of the space being available is changing over time. So it may happen that some other guy already is also coming this way, right? And that guy came, and then it decided to park here. So this is like let's say guy A, and this is the person B. So now this person B decides to park at the previous spot, or it could be like I minus 2 or something else. So let's say for simplicity just the previous one, I minus 1. So this guy is looking at this cost, but this cost itself is not giving you the full picture, because the probability of the previous space being empty, which in this case is pi minus 1, it changes with time, right? Changes with time, fluctuate over time. This is what is making this model even more interesting. So now that the person is deciding to go back to I minus 1 and park, needs to factor in this probability as well, because now it is time, let's say t, then if it decides to go back, then at that time it might be occupied by the guy A, who already decided to park here. So A has decided to park here. So this probability at I minus 1 of this being free is now 0, of the car being free, right? So probability of I mean the parking space a space being free at I minus 1 is now 0, right? And this is indeed the real life thing, right? This could, and this exactly models how things can be in real life. You are going into this big parking space, you are thinking of parking somewhere, and let's say they have put a cost price, like this is a very nice parking place with shades, and this is like the open thing, and you are looking at the cost and everything. Going back has a cost because you have to drive through, and some amount of petrol will be used to go back. But then someone else might have come already, and those places are occupied. So this is pretty much quite generic parking problem. So all this needs to be factored in the model itself. So initial probabilities for all spaces, you may say that are known to the driver. So this is in fact in if you see some sophisticated parking spaces, you will see, especially I have seen some in cities like in Europe. Then they have parking spaces, well, and then there will be a board in the parking space where in the basements they have right before you enter the parking, they have a display board. So let's say basement 1, basement 2, basement 3, and they actually tell you precisely where the spaces are there right now. Okay, so let's say you are entering the parking space, and they show you this, and they also show you pricing for this. So if you go to basement 3, then the cost of parking is a bit higher, and here let's say C2, but within B2 also they might have different parking cost. So basically in these cases where the whole parking space is shown to you and where it's free or not, then your initial probability will be known to you, right? But then as you go towards the parking, there are many other vehicles which are also trying to figure out they're going towards the parking, and some of these parking spaces may be occupied, right, which were initially free. So hence it changed over time. The probability changed over time. So so there will be some mechanism with the driver who will have some way to evolve these estimates, that how these parking spaces, these probabilities might change over time. So that's a part of the belief, right? So you are some estimate of whether those that were free are most likely going to be occupied, because you know that most people want to park in basement 1, because when you go to malls, for example, right, and then on a bike or car, then usually you want to park as soon as possible. So you think you want to get into basement 1, and then if not, then you go down to go to the basement 2, and so on, right? So so you know that the probability of empty spaces in B1 being free are much lesser in time as the time goes, because usually basement 1 gets filled very quickly, then the 2, then the 3. Okay, so these are some ways to estimate like how the parking may the probabilities may change over time. So this could be something you can factor in as a driver, what could be the possibilities. If you go around afternoon in some malls, then typically you don't even have to wait at basement 1, because by then basement 1 is, especially if you're on a weekend, on Saturdays, then basement 1 will be usually occupied and then you directly go to basement 2, because you don't even have to bother. So this will be your good estimate that I surely don't go to basement 1 and waste time, because there will be no space and I will waste my time. So ideally you should go to basement 2 or 3. So these are the estimates that you make in mind, that what could be the likely possibilities, right? But giving these possibilities to an agent, modeling these as a dynamic optimization problem, these are the real challenge we have in hand, right? We know many things from our own, we have our own belief states. These are kind of encoded in our intelligence and so on. But then to incorporate this into agents, softwares is a different game in itself, right? So we can model this problem. We can introduce some variables like let's say the likelihood of a parking space being occupied increases by probability xi, and then subsequently if it increases, then decreases by some other complementary factor, let's say 1 minus xi. Then the belief state could represent these probabilities, the vector of probability that the driver will maintain, and that the probability of the space being free at 0, probability of the space being free at time 1, time 2. So this is the time which is essentially the number of moves taken by the driver. So the fact that driver can go back also, so it will not this time will not really mean the position of the driver, because it might go back. So the position might decrease, and so here the time is about the number of moves the driver will make from one parking space to another. So so with that view, the driver has a vector of probabilities of the parking space being free or not. Okay, so up to n minus 1. And we know that the nth, if it doesn't find anything from 0 to n minus 1, then definitely it has to go to the garage. So this is the same as the previous model. So the belief state can be adjusted at each instant. So depends on what are the ways we want to update these belief states depending on the problem. So this algorithm takes into account the most recent observation regarding the state of the free and the so let us look into the dynamic optimization problem. At least it's a model for the moment. When you will code it, then you will get the full picture of how it can solve such problems. But for the moment we are modeling this. So from modeling point of view, what we have is it's a dynamic optimization framework where bk now takes the role of the state. Okay, so this belief state bk is acting like a state. And then obviously the other things are as usual, like uk is the control. So control is like you will go forward or backward, and then zk replaces the wk that we had, like the disturbance that we had. We still keep that. So this zk is our disturbance. So given the current belief and your current control that you took, whether you went forward or backward, then what is the estimated cost that you will park eventually? So this is like the whole cost, right? It's like eventually you are getting your car to park, right? Now whether you do it in other L number of steps or 1,000 steps or million steps, it doesn't matter. It goes until the end, till you terminate. So this is all the terminal from now to the terminal state, and this is the current cost. So we have seen this before. So this is pretty much the main thing here to note is that the state xk is now not changed to the belief state bk. So these are the explanations for this. So this is the optimal cost to go, starting from belief state bk at stage k. The control is uk, and g hat represents the expected cost at stage k. So because remember that this includes the disturbances wk. So this that we see here is actually expectation taken over wk. That's why you don't see the wk here, but it was like bk, uk, and wk, and this what you got, we wrote it as bk, uk. Since I have taken the average over wk, so now I can rewrite this as g hat bk uk, and f, we can denote it as a function that tells us, given the current belief state and the control and the disturbance, what would be our next belief state. Okay, so pretty much from model point of view, this is what is all we have. When you will actually implement this, you might do some algorithms. The algorithms we have seen so far are the main algorithm we have seen are the rollouts. So you can do the rollouts, and you may start with some greedy policy. You do the rollouts and see how far it can improve this and minimize the cost. So the algorithm wise, you know, one of the algorithms at least to work with this. So this is what we have said. Everything is again, so this the function fk is our belief estimator, and it updates the current belief bk upon receiving the new observations zk plus 1. But all this is decided by the cost and everything. So eventually what B I will choose will be kind of what control I will choose, and this control eventually tells me what other beliefs needs to be updated. So this is the view of f, where we're given the current belief and control, we get to the new belief and so on. And yeah, so this is all about the modeling aspects. And maybe you can write some algorithms on this as part of assignment. I'm still supposed to release some assignment. Now let us move to multi-agent problems and multi-agent rollout.
700 years into the future, mankind will leave our planet, leaving Earth's cleanup in the hands of one incredible machine. His name is Wally. After all these years, he's developed one little glitch.
Wow.
A personality. He's extremely curious. And just a little bit lonely. But all that is about to change.
Wow.
So multi-agents, we know that multi-agents are quite everywhere. Basically, even you being part of the world could be seen as multi-agent. So all of you are working in some way to achieve certain goals. So sometimes it feels like you are working on your own goal, but who knows? You are collectively working for somebody's goals. We never know. Like why are you doing everything that you are doing? So you may say that it's a very philosophical thing. Collectively, you cooperate, compete, and these are the actual words that we will discuss when we go to multi-agent in the second half of the course in full detail. There is game theoretic framework as well. So these are really complex. Competition versus cooperation, right? So these things start coming there because single agent is not competing with anyone. Single agent is only competing for the reward. But once you go into multi-agent, then who will do more and who will do less? So how will you cooperate, right? What is the division of labor? So if two agents decide to cook something in the kitchen, then who will do what? This itself is a big thing, right? If you are alone making something, then there is nothing. I mean, you will decide your own policy, what to do next. First, you cut the onions, or you do something with you turn on the cooker and things like that. So you are optimizing by yourself. But then when you're a multi-agent framework, all sorts of complexities start arising. So we do have all the tools in hand to already think about multi-agent. So let us look into some multi-agent. So there are some examples of multi-agent. Like I will do a few of these just to give you an idea of how people are writing these multi-agent codes, basically. Okay, so if you see, this is a multi-agent problem where it's a hide and seek game. So the usual hide and seek. So there are seekers. I think the red ones are seekers and the blue ones are hiders. Okay, so the goal of the blue ones is to hide, obviously. And so you know this hide and seek game, right? So you have some friends and you go and kind of hide somewhere, and your goal is not to be found out by let's say discovered by the seekers. So what are the strategies that can evolve when you are playing hide and seek, right? So in this case, they discovered that there are these blocks that could be used to kind of cover this door. right? So that it's difficult for the seekers to locate them. So this is the strategy they are supposed to develop, right? So if they keep it, so they play a lot, right? So they play a lot. They only after some time they discover that okay, moving this towards the door can really block. So now they start doing this consistently. So now the seekers cannot go inside and locate them. So this is a strategy they learned by a lot of trial. They discovered that these objects could be used for their benefit. So when they keep doing this, right, time and again, now it is the goal of the seekers to develop their own strategy that they are losing, their reward is not really great. So now they think what they can do now. So they discovered that there is a wedge here, and whether they can use this wedge in some way, right? So now they discovered that okay, they could use the wedge, and they pull this wedge there, and they can go over that wedge, and then they can find this jump over, and they can find these hiders. Okay, so now at the next strategy that the blue ones learned is that these guys keep using the wedge, so let us pull the wedge inside and then block this so that they will not be able to come inside. So these are intelligence that's supposed to be kind of like as humans you will try to do that, right? So the whole point here is like, can these agents also learn to develop these strategies, right? And so this is why RL or sequential decision making or dynamic optimizations, or dynamic optimization is like a broad framework of sequential decision making, and within that special one is RL. So then you can complicate these environments a lot more. Okay, so you may have different scenarios, different type of rooms, different objects, and then they are kind of hiding, and these guys know how to move these blocks and jump over. So all kind of strategies evolve on their own. It's not like someone is telling them. It's purely reward based. Okay, that's the power of this. The whole idea of the DeepSeek, the power of reasoning that the DeepSeek has recently proposed, is a Chinese startup, is that their whole conclusion was that it's purely RL applied to chain of thought can let them discover new ways to reason about maths problems and so on. Okay, so RL in some way allows you to generalize or build the strategies. LLM can help you with the predictive task, pattern matching, but for coming up with strategies, you need some reward-based models like RL, okay, for decision making. So so this is pretty much. But here, from our perspective, this is a multi-agent framework where they where two agents on each side are competing, and so this depends on the goal at hand. And then within each group they are cooperating. So red ones is cooperating with each other as a team, and the blue one is also cooperating with each other as a team. Okay, so these are the things that you see in mostly in multi-agent, when to cooperate and when to compete, right? So this is now DeepMind, which primarily was working mostly on RL, and initially they were playing a lot on games, right? So they did all this stuff like AlphaStar and all this. So this is Google DeepMind in London, and this startup was mostly, and initially it was mostly focused on like RL stuff. So they use this again. This is a multi-agent framework where they developed RL framework to play these multi-agent games. Okay, so if you know StarCraft, then it's kind of a fighting game. I have not played that much myself, but it's like a shooting game.
The swarm brought ruin to our world. Our proud people became refugees. And yet, they could not shatter our unity. For we are bound by the Kala, the sacred union of our every thought and emotion.
Blizzard and the StarCraft 2 team has worked really hard to create a special version of StarCraft 2. We've actually released to the public some tools in this version of StarCraft 2, but also worked very closely with the team at DeepMind. It's not exactly the same version of StarCraft 2 that players get at home. It's got the same rules, but it is geared towards AI research. And there's some very important differences. I should mention that because we've geared it for research, it really isn't set up to do things like live observing. So the games that we're going to watch today will be from replays, and watching live games, we have to watch from the player perspective.
Okay, and Oriel, to jump over to you, why does DeepMind look at StarCraft as the next game, the next thing that you want to kind of pursue and make an AI for?
Right. So, well, first and foremost, the mission at DeepMind is to build an artificial general intelligence. And to do so, it is quite important to benchmark how our algorithms, or our agents, as we call them, perform on a wide variety of tasks. So these tasks, there's quite a few of them that we've tackled in the past, Atari being perhaps the first video games that we kind of started from, as well as Go, chess, and many other games. And then for us, StarCraft afforded some pretty unique sort of research challenges that were for us kind of the obvious choice as a kind of a next step for our agents to perform at a very good level. And the one perhaps that I would highlight from this graph we're seeing is the fact that in StarCraft, you don't see the board all the time. There's this notion of imperfect information, as you probably know. And so, yeah, so that means that an agent must kind of predict, estimate what the other player is doing all the time. And there's all sorts of interesting things that emerge. And perhaps the other obvious one, as opposed to perhaps Go, is like the fact that it's real time. So you really must act now, otherwise you might lose the game. So those are a few of the highlights of why StarCraft is such an interesting research challenge for us.
Well, you guys announced this project a little over 2 years ago. So can you fill us in on what's been happening in that time?
Yeah, for sure. So actually, StarCraft is definitely not, we're not the first ones to realize the importance of this as a domain for AI. And in this timeline, we kind of see that the history actually stretches for over 15 years or so. In fact, it was in 2003 that it was first sort of advocated that RTS games could be actually used to push the boundaries of AI. And then perhaps another kind of key moment was back in 2009, where the community, the open source community, has been incredible. So they open sourced a tool for you to connect to StarCraft 1, the first version of StarCraft. And ever since then, there's been quite a few of activity in terms of AI versus AI tournaments. There's been quite a few of them going on for the last 8 years or so, where kind of people have built bots or agents to play the game and perform well. And that's been an incredible, exciting place to be. In fact, I used to, I participated in the very first, version there, like the 2010 competition.
Oh.
And I actually tested the agents, so I was asked to be the professional gamer to play against them. So that was kind of a fun kind of throwback.
Yes. So this is AlphaStar. This is an AI that we don't know how good it is yet, and we'll go over some of the fine details of the game. But already we have some interesting things happening for a Protoss versus Protoss. You notice that up here, TLO is making buildings right at that small choke point, that small ramp.
Mm-hmm.
This is a tactic that we use in Protoss versus Protoss to make kind of a wall so that your opponent can't get into your base. But AlphaStar is skipping that altogether.
There are very few Protosses in Europe that don't wall off. I like to think that I'm one of them. Now, what you guys can maybe ask yourself, what's the benefit of not walling off? Technically, you save a little bit of money. Like, you save a few resources, because that's a lot of probes, by the way, just chasing around. This is not optimal gameplay, I think, then.
No, that's
quite a few probes. Technically, you can say it's scouting, but that's a lot of probes bouncing around, and at the highest level of StarCraft 2, we like to think that we're all very efficient and very clean with our build orders. So every probe that can be gathering resources early on, it's very worried about cannon rushes, it seems like.
Yes. Yeah, and a cannon rush is kind of a very aggressive early game strategy that could be used against it, but TLO, we can see, is not going for anything like that. Now, in the meantime, we have all these probes. They're just kind of gathering resources, minerals, and gas to build these buildings so they can build units to get out on the map to control area, much like any board game that you might see. But it's just, I'm so interested right now because I see, for instance, TLO is making to adepts.
Yep.
And this is the main reason why you'll make a wall at your ramp, so that those adepts can't come in and start to destroy your probes.
Nope. Even though the AlphaStar has created kind of a nice SimCity, right? There's a little bit of a circle around the mineral line, so you can say that the workers are somewhat protected. In general, especially since TLO used double chrono boost, that's an ability of the Nexus, which makes you build units a little bit quicker. In a regular game, if we are casting this in a normal way, we say that these two adepts of TLO are guaranteed to kill 8-9 workers. And in StarCraft 2 terms, that means that you are incredibly far ahead. If you can pick up that many workers of your opponent early on, you are going to be very far ahead.
Well, right now we see the adepts using their shade ability to get in here and start attacking probes. You see that TLO is already eliminating some of these workers. Now, AlphaStar is trying to target them down as best as he can, but this is pretty significant damage, I would say.
I must say this is a really interesting exchange, because even though Dario was able to pick up 4 or 5 probes there, which we normally say is a very big deal, you could say that the maximum amount of workers that you want to have on your minerals in this phase in the game is 16, maybe 18. AlphaStar technically still has that, at least. It's mining a little less gas, but when it comes to mining minerals, it's still mining more than enough, and it did pick off 2 adepts. So I wouldn't say it's the greatest start for AlphaStar, and don't think it's the cleanest or most optimal start, but it's also not game over by any means.
Yeah, its balancing of the economy is very interesting, because, for instance, there's only 2 workers on gas on one of these geysers, 3 is optimal, and, AlphaStar is skipping that. TLO comes in again, is harassing more of those probes, killing them off, and, I feel like it's a good position right now for TLO overall.
Yep, but it seems like his units are a little bit out of position to keep these two. Look at the micro.
Wow.
AlphaStar actually getting quite some damage done. That evens up the score.
Yeah. Well, the worker count we can see at the bottom right now is 24 workers for TLO and 25 for AlphaStar. So overall, I guess AlphaStar has recovered from the early game.
Yep. Normally losing 10 probes in a 4-minute and 25-second game, that's way too many. We'll say that that's too much damage. That's not, you're not supposed to take that much damage. But this game is not over by any means. As we saw, AlphaStar is also going for the robotics facility. Is getting a warp prism. This warp prism is going to allow AlphaStar to be aggressive on the other side of the map and should be able to pull off some pretty nice micro, I assume.
Yes. Now, this strategy in particular is really, really micro-intensive, as you said. You have to control your units just very precisely, which we've already seen that AlphaStar is quite good at. You're going to be kind of juggling stalkers, these big long-range shooting units in and out of the warp prism, trying to dodge taking damage and doing damage to your opponent in the meantime.
I love how AlphaStar is truly respecting the Oracle as well. So he knows there is an Oracle out, we'll just leave a couple stocks at home, but at the same time still try to make something happen on the other side of the map. And this is actually kind of scary for TLO because, Phoenix is about to come out soon, but once again, this warp prism is going to allow AlphaStar to micro these units incredibly well. And I mean,
Well, so far the micro's good. It's not like perfect micro that we're watching at the moment. But look at this. Bending backwards, kind of kiting everything with these stalkers. Some good juggling going on. That War Prism's still alive, though very low on health.
yeah, a couple of stalkers are very low on health as well. Nice pickup there on the Oracle. So both air units went down for TLO, but still has an expand. Is still trading out quite decently, I would say, in the middle of the map. But if you take a look at the army supply, the army of Alpha Star is actually quite a bit bigger now. Obviously, we left 4 or 5 units on the other side of the map.
Yeah.
So those units can technically join for the next push. And since the shield battery went down for TLO as well, this can actually get a little bit dicey.
You're quite right. Even though TLO right now has an economic advantage having 2 bases to 1, I don't know that he's going to be able to hold this assault from Alpha Star.
I think this is maybe a moment where you can see that TLO is not a natural Protoss player, because I think the start was good for TLO, and I think there was time to be ready for this. It's still not over, but the army of TLO is very small compared to the army of Alpha Star.
Yeah, the TLO is in a dire position right now. These stalkers just going in and out, dodging all the damage that TLO is trying to give to him, and kind of choosing when to take these battles. It feels to me like so far these attacks have been very well planned by Alpha Star.
And they're relentless. Does not stop. I mean, Kim said he was worried that perhaps the Alpha Star was going to be incredibly turtly. Well, it seems like the opposite. Turtling is a term we use for a player that just never attacks. I think safe to say that Alpha Star is the opposite. It loves to attack.
Well, that is it.
Right. So if we look into multi-agent, so let us quickly work through some of the ideas how we can actually write these algorithms. So first, let us quickly define multi-agent. So multi-agent system is viewed as a collection of decision-making entities compared to single agents, aiming to optimally achieve a common goal. Agents accomplish their objectives by collecting and exchanging information and interacting with each other. So agents may be obviously software programs for us. It could be like robots. So what are the challenges? Challenges in efficient implementation of multi-agent includes limited communication, lack of fully shared information due to limited bandwidth. So sometimes it may not be so easy to even communicate. Okay, noisy channels. Let's say network you were working with failed, and you still have supposed to continue taking some decisions. The lack of synchronizations. As the number of agents increase, the size of the set of possible joint decision grows. So this is also some additional problem. Earlier we had one agent and so many controls decisions to take. Now there are multiple agents. So the joint state action space is now huge now. So if you want to do some look ahead minimization, then obviously this creates some challenges. So this is the framework of multi-agents, where we have agent 1, agent 2, agent 3, 4, so on. They can share information across each other, but then there is also an environment. It could be room, it could be some place where they are going through. It could be robots, collection of robots going out in an environment. So that could be the environment with some goals and objectives to achieve in that environment. They might share the information to the environment as well, or within themselves as well. So there are multiple agents, 1 to M in this case. They have their own controls. So now we have controls for each agent. So we call it superscript L. So U superscript L is the control taken by the agent L. So at each stage, they can exchange new information. They select the decision variables for each stage. And we can consider the discounted infinite horizon problem, where the control can be now written as a vector, where each component of the vector is a control of each agent. And we consider a separable structure where we believe that each control is taken by an agent and it comes from UL of X, the control space of the Lth agent. So this is for each agent they have their own control space. Okay, so capital UL, and then the control constraints set overall is coming from this. So this is basically a Cartesian product of controls for each of the agent. So agent 1 has all possible controls. Agent M has all possible controls. So if you take a Cartesian product of them, so you get an order pair of controls like this. So it's obviously it arises in distributed decision making. So each component UL L equals to M is chosen from UL, and assume each set UL is finite for the one-step look-ahead minimization of the standard rollout with base policy. So we may want to do the same like we did before, and we may assume that the control space is finite. So basically UL is finite, and we may do one-step look-ahead minimization, and there is some base policy for all the agents. So we need to elaborate on this in the multi-agent setting, how the base policy is defined, and then how they can do rollouts. So in the multi-agent setting, as such, everything looks very similar. It's just that the U can be a vector now. It's a vector of length M, where M are the number of agents. So U is a vector now compared to single agent, where it was, as such, it was kind of a scalar. Okay, but it may be a vector there also. But here the vector, it means like each component belongs to one agent control. So so this is what we have, and then if we look into the multi-agent framework, then the possible key factors that we may need to compute is n to the m, and this is the problem we have, right? There are m agents, and each agent have n controls in hand. So this kind of leads to, so now there are like m agents, like 1, 2, 3, and then m. Each agent now have n controls, right? So then you have n and n collectively. These guys also have like n possible controls, and so on. So you have n times n times n, m times. So in a multi-agent setting where there are m agents, the total control space, or let's say the corresponding Q factors, is n to the m. So this is pretty high in this multi-agent setting. So standard rollout algorithm will require an exponential number of Q factors, and which can be overwhelming, right, even for a moderate m. So the computational overhead motivates a more efficient kind of rollout. So can we do better? Can we have a cheaper variant of rollout, right? So so what we can do is that we can do one step look ahead minimization is replaced by m successive minimizations, one agent at a time. Okay, so rather than saying that all the m agents are going to pick controls from all possible configurations of these controls is n to the m, which is quite huge. What we want to do is that we want to make agents take decision one by one, and they will do m times. Okay, so they will take decisions one by one. So there are m agents, so they will do it for m times, and each agent has, let's say, n controls to decide at a time. So then the total will be n times m, not n to the m. Okay, so what is the scenario right now? So if I have to explain this again, so let us say you have agents, 4 agents, right, and 3 controls at a time, right? So 4 agents, A1, A2, A3, A4, and each of the agents can take 3 controls. Okay, so let us say 3 controls at a time, each agent. So A1 has 3 possibilities, A2 has 3 possibilities, A3 has 3 possibilities, A4 has 3 possibilities. So at a time, at a given time, what are the possible ways they can have? So basically it is according to this n to the m. So basically 3 to the 4. Okay, so 3 to the 4, it's 81. So there are 81 possible controls to take, where each agent as a whole, you can think of each agent as a big agent, right, combined of these 4 agents, and they want to do go to the next state simultaneously. So now to do that, there are this many possibilities, 81 possibilities, and out of 81 possibilities they will choose. So they have to look at the 81 possibilities, 81 costs they have to kind of check, and then out of that, whichever was the minimum. So this is a tuple, right? So tuple of 4. So tuple of 4 is there. So there is 1, 2, 3, 4, and this tuple is being collected from the space. It may not be real, but let's say some space of dimension 81, right? So this many. So U1 can take 3 possibilities, U2 3 possibilities, U3 3 possibilities, U4 3 possibilities. But I want to take this one tuple, and that should be calculated out of the 81 possible combinations of these UI used at a time. Now this is quite huge, and we are in a modest case where there are only 4 agents and 3 controls for each agents. This still went up to 81, and this is just to do one step look ahead to identify whether I should go to the next step, and then again I have to look for another look ahead. So what are we planning now is, rather than thinking of all the agents and then doing a look ahead as a next step, let us change this to one agent at a time look ahead. So now what we want to do is that we want to say let A1 select its control first. So if A1 selects its control first, then A1 has to decide based on the 3 moves. Okay, so based on the 3, A1 decides So then let us say A1 decides with this. So A1 has to choose from three possibilities, okay, because there are three controls for A1, and then A2, but all are at the stage K only right now. So A1 has decided, so it's done. So then we come to A2. Then the agent A2 has three possibilities to decide, and this agent A2, let us say, decides on one of the controls, like this, and again A2 has to decide out of three possibilities. So then similarly we continue this this step. So let us say A3 and then A4, and each had let us say, it's not necessary that they have three controls each of them. Some agents may have more control, some agents have less control, but we may simplify, and for the moment let's say 3. So then out of these let us say the agent A3 decides on this, and agent A4 decides on this. So our trajectory is this, 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 and this, all for the state K only, right? So at the K state, we now let these agents decide one by one, and there are M agents, so they decided M times, right? So that way, the number of cost reductions is now we have to compute the cost here 3, 3, 3, 3. So 4 times 3, 12. 4 times 3, 12, and then we go to the state K plus 1 next. K plus 1, we do the same thing. A1, A2, A3, A4, again 12 cost computations. Whereas if we go here, one step look ahead is taking me 81 cost computations, and then decide which one to take. And then next stage again I have to do 81 computations, and then to decide. Now you may say, isn't this better because we do simultaneous, because we have looked at all possibilities simultaneously and then decide which one to take. It turns out that this is not bad at all, where you let one agent decide and then other agents decide after that. So sequential is, for many problems, is not that bad. It solves many of the problems cheaply. So this is our plan to reduce the cost computation, and it works fairly well. And it also learns strategies of like cooperation and things like that. So it is not at all bad. So what we want to do next is to develop this framework of multi-agent rollout. And multi-agent rollout means that the first agent, 1, it is choosing its policy mu tilde, and we call it tilde because it's kind of an, let's say, approximate policy. If you want to think of these as simultaneous thing, then you may say those are like the exact ones where all are deciding all possibilities right now. But here we change it to like let one decide first, then I will decide, then I will decide. So there may be a latency on that. Maybe you may say that okay, someone is deciding, and then after the agent has decided, then you decide. It doesn't mean that the agent will complete the work and then you decide. It's not like that. It's mostly about the decision right now. Agent has decided to do something, the agent has done something, then the second agent will decide something. The agent is not waiting for the work to be completed with the first agent and then decide. So decision and doing some work is a different thing. So they may parallelly work on many things, but the moment you see that this guy has started doing something, then it's not worth for you to do that maybe, and you decide on something else, right? So that way they can still like do simultaneously many things. So here agent 1 has decided based on the possible controls that the agent 1 has, and then it is trying to minimize this expected reward, and the other policies of the other agents are fixed. So this policy of the agent 2, agent 3, agent M, as you can see here, so these are kind of fixed. Whatever the base policy the other agents have, those are kind of frozen. So it's only agent 1 is deciding right now. Then the agent 2 will decide. So agent 2 will indeed take into account the policy of the agent 1. So you see the policy of the agent 1 was decided here. Now this is taken into account here, while the agent 2 is now going to. So agent 2 does have a knowledge of the decision taken by agent 1. So this is the updated policy which agent 2 is using, and then other things are frozen for other agents, and then the agent 2 has decided, and this can keep going on. At the mth stage, the agent M is deciding its own policy, and then all the policies that has been learned until now from 1 to agent M-1 is being used here, and after that the agent 2 is now deciding to minimize the cost, and hence a good policy to take. So each agent component UL is obtained by minimizing with preceding agent components taken into account, and those are fixed when the agent 1 is deciding. So following agents UL plus 1 to M are fixed at values given by the base policy. So for the future, for next set of agents, they are frozen with the base policy mu. So this algorithm, as I described in the previous slide, it only takes O and M because we are going one agent at a time. So hence, if there are M agents and there are N controls for each agents, then we only need to compute O and M Q factors. So which is way less compared to simultaneous rollout, simultaneous look ahead, which is indeed O n to the M. So this is the idea behind multi-agent rollout. So we have a state X, and we let the agents 1, 2, 3, and so on up to M take their own controls decisions, and then we arrive at the next state, which is X bar. So this is pretty much what we have done. So basically, we can also see these states as some intermediate states where we have XU1 as the first state. After the agent takes the control, and then agent 2, and so on. So we may think of these as kind of some K. We can think of these as kind of some intermediate states, right? So okay, so so these are the kind of cost to go functions that we generate out of all this, and we may prove that the multi-agent rollout does achieve a cost improvement over the base policy. Okay, so if you do it this way, then it will improve upon the base policy, which is typically a greedy policy. So under certain assumptions. So okay, so it can be used in policy iterations and so on. So let us see an example to conclude today's lecture. So we have like 10 minutes to conclude. So let us see spiders and flies example as a multi-agent problem. So let us see this problem where we have spiders, which are these guys. Spiders, and then there are flies, which are these guys. Okay, so obviously we know that the spiders want to eat the flies. So this is a simple problem where there are a set of spiders trying to kind of kill the flies. So this is a multi-agent problem where the spiders need to take decisions, and in this case the control is like up, down, left, right, or stay. So there are like 5 possibilities for the spiders to move. This problem can be made more complex where the spider and flies, of course the spider is moving towards the fly, but the problem can be more interesting when the flies are also allowed to move at each time state. So basically flies don't stay at one place. So at time now the fly is there, but then next time the spider moved towards the fly, but the fly also moved. So this makes it more interesting problem to solve. For simplicity, you may assume that the flies are there maybe. Okay, so that's the simplest one. So there will be assignment on this. You will be doing that, where you will kind of solve this problem. You will code and solve this problem. So of course, if you look into this example, then in this specific example, you can see the complexity involved. There are 20 spiders, and there are 5 flies, right? And these 20 spiders are supposed to move. So there are like 20 agents. So this is your M, and the possible moves that you have are like 5 of them: left, right, up, down, and stay. So the controls here are 5: left, right, up, down, or stay. The spider may decide to just stay also, right? So there are 5. So this is like 5, 5, 5, 20 times, because for each of the agents there are 20 of these. Each have possibilities to take any of these controls. So a simultaneous look ahead will be 5 to the 20, but obviously as we planned, we want to do it in a sequential way. Let one spider make a decision. So one spider makes a decision. There are 5 possibilities. Takes the decision. Then the second spider is going to take the decision. After that, another 5 possibilities, and so on. So it's 20 times 5, which is much cheaper than 5 to the 20. So the objective is to obviously catch all the flies as fast as possible. During the stage, each fly moves according to state dependent probability distributions. As I said, the flies can move as well, and this is indeed more complex version compared to what I'm going to give you as an assignment, where the flies will be staying there. Okay, but it will be more interesting when flies are allowed to move as well. Okay, so you will try to do this, but I will give you some ideas initially, right? So each spider learns a state. at the beginning of stage and can move to either to a neighboring location, stay put. So as I said, there are like 5 possibilities and so on. So this is a repetition of what I said. So for multi-agent rollout, as we know, we always need some base policy. So base policy, you may decide to be a spider going to the closest fly. So this is the greedy policy that we know. In the shortest path problem, we said that there are multiple cities, so I will go to the nearest city. So this is the greedy policy, right? So here again, you can think of the same way. Maybe the initial policy for all the spiders is go towards your nearest fly. So this is your greedy policy. It may not be the best policy. We know that the greedy policy are not necessarily best, but let us say this is our base policy: go to the nearest fly. Okay. So then we can kind of try to do this this rollout and see what we get out of all this, right? So this is time 0, and this is a simplified problem. And what could be your base policy here? Base policy is a greedy policy, right? So base policy being greedy policy means that each spider will decide to go to their closest fly. Okay. So we basically here you have to count what is the closest distance, right? So let us say this is like 1, 2, 3, 4, 5, 6, 7, 8, 10, 11, 12, 13, 14, 15, right? And if it goes this way, 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12, 13, 14, 15, 16. I hope I did this correctly. Otherwise, it will be 15 on both sides, right? In that case, they will kind of do a coin toss and approach to anyone. If there is equal distance to the flies, then it seems like there is equal distance for this fly, and the greedy policy needs to be followed. So it will approach like this. Let's say coin toss. It could have gone this way also because there was the distance was the same, but it seems that this spider will go definitely this way. And I think let us make this spider go, otherwise it seems like most will go down, right? So there is let this spider go one step there, and this spider, I'm not sure. For the moment, let us assume that the shortest is like this. Okay. For this spider, let's say the shortest is this down. Okay. So this is what they will do at the current time. They follow a greedy policy. They will move one step. Okay. And so this is greedy policy. The greedy policy, they will at some point go and maybe catch the fly and so on. But is this the best policy? That is something we want to know, right? So greedy policy may not be the best. So in this case, let's say at time 5, then we see the position of these flies. I mean the spiders. So it seems like apparently they moved here after 5 time steps. Okay, and then at the time 24 step, one of the spider caught the fly. Okay, so one of the spider has caught the fly, so that is gone. That fly is dead. So now the others will now that the state of that fly is gone. So now there is no incentive in going towards that fly. Now they will think about this fly. Okay, so now they will move towards that fly. And so again in these problems, as you can see, they can do a simultaneous rollout. So they can look at all possibilities for each of them and then they move, or they can go one state at a time. Now now this is the base policy, right? So this is base policy where they are going to catch these 2 flies, but then the next step is to improve on the base policy. So how will you improve on the base policy? So here let us focus on this agent, right? So to update the base policy, they have to we will go with the multi-agent rollout, meaning one agent at a time. So now this agent, by definition, by the base policy says that the agent should go, this spider should go down. Okay, this is the kind of closest to the fly. But what we do in look ahead is that we don't necessarily go with the greedy policy. We explore something else. So in this case, this spider may say, no, I don't want to. I want to kind of explore the greedy policy and see what could be the cost if I do follow the greedy policy. If I don't follow the greedy policy, so then the spider may decide that what about this? Because this is what you do in look ahead. You explore other possibilities. What about this? And what about this? So this will be part of the look ahead. And green was the base policy where you go shortest distance, and the base policy is saying let us explore something other than the shortest distance. and what could be the cost estimate if you do take this decision. Okay, so let us say for the moment that this decision was taken, which was different from the base policy, which was green. Now this agent, first agent, has taken its decision. Now the next agent will take a decision. So let us say the next agent is this one. So this agent will, again, according to the greedy policy, the agent should go to the shortest. So they cannot go diagonally. So let us say the shortest will be like this. But then this agent is also now doing look ahead. So these are the possibilities for this spider to explore. So now out of these explorations, maybe this spider will say, okay, let me take this one. So this is look ahead. So this is done. Okay. So this agent is taken some action. This agent has taken some thing, and then other agent will also do the explore the cost. So important thing to remember here is that each agent is deciding on the look ahead. Their current action, which is away from the base policy, only after it has done the cost estimates based on other agents' policy which are greedy. Okay, so this is a bit mouthful. So let me explain this minor detail here. So what I'm trying to say is that when this agent is trying to do a look ahead, and let us say this is the first agent, then this agent it knows that the base policy of this agent is to go down, but this agent is doing a look ahead, so it is exploring other things. So for the exploration, so these are the possibilities for this agent, or to stay also is one possibility. Now to decide on these red moves, it will do its cost estimate. So basically with this other agents will play until the flies are killed. Okay, so to do this cost estimate, so let us say this agent has taken this move. Okay, now other agents will follow the base policy. Okay, so other agents follow base policy, meaning going to this, fly got killed, this. So maybe this guy fly got killed before, this went there maybe, and then whatever is remaining, they will move there. So you will play this game until the end and calculate the total number of moves that you needed to kill all the flies, just so that you can decide on this. You see what I'm trying to say? Just for the current agent who is exploring with the look ahead, this agent is assuming that all others will continue to follow the base policy until all the flies are killed. Now, given the cost estimate of that, did it improve on the base policy? If yes, then the agent will say, okay, now my idea of exploring is a good one. So it updated its policy now. You see, now the second agent will do the same thing. So second agent, now this is now there. Okay, so this agent has taken a decision, so it moved here basically. This is spider, now you have to think that this is there. Now let us assume that the second spider is our second agent. Now this second spider has a base policy which is to go to the nearest. So this spider will has these possibilities to explore. Okay, now it will look at this. Now it has to do the cost estimate, right? Because this is in the DP form that you have to do this J star thing, and it is assumed that the first spider has moved. That's the updated policy, mu1 tilde that we saw in the expression. Now just to decide on this, it will now play out the greedy policy for each spider. So this spider will now follow greedy policy. This spider will now follow the greedy policy, and so on. Okay, so others will follow the greedy policy. And if the two flies are killed in a minimum number of moves compared to its own greedy policy that it was taking, then it will decide to update its policy that this was a better move. So then this has moved. Then the third spider will do a look ahead. So, and if it is not, then it will explore the other possibilities of going in another direction. So that way you can see that to do this cost estimate, this thing has to be played out until all the flies are killed, just so that one agent can decide on their current look ahead possibility. So this is something you will do, because you don't have to do it. Maybe you will write the code, and the code will do this repeated cost calculations for the look ahead in the multi-agent setting, and then finally you will learn a policy where these spiders has learned how to move optimally in a way that in minimum number of moves, both the flies get killed. Okay, so this is this was one step look ahead. Now you can see they could have done 2-step look ahead for a better view. Usually it improves. So when you code this, you will get a better idea about and get a better feel for how these algorithms work, right? And okay, so with this, I think spider problem I can stop, and see you next time.